Hey guys, my name is Hiraku Murakami with NovaEdge Academics. Welcome back to another video. This is the last video on topic C3 wave phenomena. Again, like last video, this is an HO only topic. So if you are an SO, then you do not need to know these stuff that I'm going to be explaining, okay? So just a quick recap. Until last video, we did double slit interference, right? We had two wave sources and how they interacted. We also had single slit interference, and I explained to you why it happens. And I also explained how they combine with each other, right? So we've covered basically the very basics of single slit, double slit. Now I'm going to talk to you about multi-slit diffraction. So the question is, what if I make the number of slits 4 slits? So now I have the waves with, of course, the wavelength. And now I have 4 slits. So I'm essentially going to have 4 wave sources, and they're going to interact. Same principle as double slit. I'm not going to draw it all out. Now I want you to think, okay, how does it even look like, right? How does the interference pattern look like? Well, it looks strikingly similar to double slit. In fact, it looks very, very similar to it, except there's a few differences. So this is how the graph looks like. It looks quite similar to double slit, right? Except there's a few differences in the sense that it looks sharper, like it looks thinner, right? This guy looks thinner. Okay, why is it thinner? Well, because the probability of all 4 of them overlapping at the peak is quite small. So that range where you get the really maximum constructive interference between all 4 wave sources is very, very thin. It's also the same for these secondary maxima. We get these emergence of 2 secondary maximas. What are these? Well, they're like sub-maximas, right? They're smaller. That's what happens when you have less than 4, right? Because there's 4 wave sources, maybe 3 of them were overlapping with each other, and the other one was destructive, right? So you have 3 and then 1 working against it. Now we get these smaller ones. Okay, so these are the emergence of happens. Now, one thing to note, the intensity is 16. Okay, the intensity, if you have 1 slit, it's actually 1. If you have 2 slits, then 2 amplitudes combine with each other, it makes it 4. If you have 3, it's 9, and then if you have 4, it's 16. So what does that mean? Intensity is the number of slits squared. Okay, and why is it squared? Because remember, constructive interference amplitude adds with each other, which means amplitude, they just combine, right? But intensity is actually proportional to amplitude squared. So let's say I have 2 slits. That means I have double the amplitude, leads to 4 times the intensity. What if I have 3 slits? Well, I have triple the amplitude. They combine and make it triple the amplitude. That means I have 9 times the intensity. Okay, so that's the relationship between intensity and amplitude. Okay, now, do you need to know all of these stuff? You really don't. This was more in the past curriculum. They made it simpler and easier in this one for wave phenomena. Of course, you guys have, more difficult stuff like relativity and thermodynamics that it was an option for us to explore when I was my time to do physics. So now the question becomes, what if I increase it to 20 slits? Can I continue to see this pattern? And the answer is yes, you can. In fact, the intensity becomes 400 because it's 20 squared, right? And then also it becomes much sharper, so it's much thinner. It looks more like a line now rather than like a curve, right? So it's like a very sharp intensity patterns here. And then the rest, there is secondary maximas. You just don't see it because they're just too tiny. Okay? Now, pop quiz from last video. I hope you understood from last video. What are the differences between this graph A and this graph B? You pause the video and think about it before I reveal the answer. The answer is they are different in the individual slit width B. If you recall, theta is equal to lambda over B, right? That's the angle to the first minima of single slit modulation. This is a single slit modulation. It's the blue line, right? And because B is different, the angle to the first minima, that's the angle, by the way, is different because this one is not even on the graph. It's much bigger. So if angle here is bigger and angle here is smaller, that means B is smaller in here and B is bigger in here. Okay, this is a typical way for them to ask you a question in paper 1, multiple choice, right? So you only have 1 minute to basically think about this concept. So just practice, okay? Now, how about more than 20 slits? 20 slits looks like a lot, right? But what if I have more than that? Well, that's actually where we get to something called diffraction grating, because diffraction grating has way more than that. In fact, the rating that they tell you is something like 600 lines per millimeter or 600 rulings per millimeter. And you need to know this because diffraction grating comes in your paper 2 and paper 1 as well. But what does this lines per millimeter means? This actually means they have 600 slits and 1 millimeter span. So if I have a ribbon of 1 millimeter, they have 600 slits of them. That's a crazy amount, right? And this way you can actually find the slit separation, D, because D is just 1 millimeter divided by 600 lines. So that's what? That's 1.67 times 10 to the power of negative 6 meters. Okay, that's D. Okay, so just by knowing this rating, you can find the slit separation. Really important stuff, by the way, that it's not really looked in detail in your textbook or probably by your teacher. Okay, now if this is true, then the intensity pattern probably looks insane. In fact, it probably looks like this is a single slit. It probably looks like sharp lines, right? Sharp lines, similar to how we observed the 20 slits, sharp lines, but even sharper, because this is 20, right? 20 slits. Well, this one has 600 in 1 millimeter. So if I have, a diffraction grating that's 5 centimeter, that's 50 times 600 slits. That's a crazy amount, right? And you might be asking, okay, why do we have this device? Well, it's because it allows us to separate colors really effectively, right? When we have a white light coming in, it has all sorts of wavelengths. It has infrared, it has visible light, it has ultraviolet, right? Especially visible light, we want to see it separating colors. And the colors that separates, the red one is like 750 nanometers, and the violet is like 400 nanometers. Okay, what's the math behind tying this whole separation thing? Well, this angle here, I'm actually going to use a first order. This angle here and this angle for the red one, they are different. Why? Because d sine theta is equal to n times lambda. So first order, n is equal to 1. So I can just ignore that. So that's going to be lambda, right? So depending on the lambda you have, whether that's 400 nanometers or 700 nanometers, by the way, d is the same, right? So depending on the lambda, theta changes. So how much it diffracts changes. Okay, this is really important. That's why we have this really colorful separation. And okay, you might be asking, why do we need that many slits? And it's because if we have so many slits, then it's very distinct. It's very sharp peaks. If it wasn't, then they would be overlapping with each other. The purple would maybe be like that, and then the red one would be like that, and they'd be overlapping, and it's really hard to see. Okay, so that's the use of diffraction grating. You will get questions on this. So let's do practice problems. Pause the video and give this one a try. Okay, so they gave us rulings per millimeter. So D is 1 millimeter over 600 lines. Okay. What is the angle separating the central maximum? By the way, they already gave us a wavelength. So what's the angle? In this case, I'm going to evaluate at n equals 1. .24°, okay? Now, second part of this is how many maxima can be seen, okay? Now, that actually digs down into this whole d sine theta is equal to n lambda. So there comes a point where this doesn't mathematically work because this portion becomes greater than 1. Okay, and you can't take the inverse of sine of something greater than 1. So if I set that up, I get 2.46. So rounding it up, it's the third maxima. At that point, I can't see anything. So I can only observe 0th, 1st, and 2nd. Okay, third one doesn't exist. Okay, this is also really important in paper 1 stuff. Okay, let's do another example. Pause the video and give this one a try. Okay, so we need to explain why red light in the second order spectrum overlaps with the blue light in the third order. So if I had a third order here, it would probably look like this. And the reason why it overlaps is, well, that's what happens when you have violet, where that, if I solve for the angle, I get a value that's somewhere in this range. And then for the red, I do the same thing. Well, I'm going to do the second order because they're telling me why do they overlap with the second order. Right? And I can actually compare. So I'm going to do it for the sake of showing it. So I'm going to use a value from the previous video, 600 ruling, previous question, 600 rulings per millimeter. Okay, so lambda, I'm going to set violet as 400 and red as 750. Okay, so this is what I get. So I guess you can see that this angle is greater than this. So this angle in the second order is greater than this angle in the third order for violet. So you can see how the change in wavelength, the difference in wavelength can affect this much. Okay, maybe if I did 700, it would be a bit closer, but the answer to this question is due to the difference in wavelength, where the wavelength of the violet is smaller, significantly smaller than the red one.